So hello everyone. We are here to record the seminar on the project we did on graph-based analysis on social networking site by using the shortest path algorithm. So our group includes me, Athar, and Arnav Gupta. So what is our problem statement? So we are given a graph of interconnected nodes of a social networking site. So our main agenda is to find the shortest path from starting node to all other nodes. And we have also added the real-time update by using dynamic graphs. So this is about our data set. We collected our data set from the website Snap, and which includes nodes and edges. So the key challenges we are facing is the scale. The graph is large and contains thousands of users. Second is the real-time updates. The graph will also change dynamically according to the new connections and friendships. The third is the edge weights. The connections can have weights indicating the strength of the cost between the each user. So the use cases. The first is the social network analysis. So by identifying the shortest path, we can also suggest our friend understanding their community structure. Second is recommendation system. The third is routing and navigation with real-time. So these are the algorithms we have used. The first is the Dijkstra. Its purpose is to calculate shortest path from the source node to all others, but it has limitation that it cannot handle the negative weights. Now we will see the Eclipse code for it. So this is the Eclipse code for it. So first we have created a class named graph algorithm, which includes the basic structure of how a graph is implemented. So from line 20, we have created the function for loading the graph, basically parsing the file. And here we are also skipping the lines which contains null values or the lines which have not complete information. So till here, our parsing is done. So we'll come to the Dijkstra. So basically, Dijkstra works on the data structure of heap. That is, we are implementing through priority queue. So while the graph is not empty, it will implement all the functions. Now, Arnav will continue with the Bellman-Ford algorithm.
So Bellman-Ford algorithm, the purpose is it calculates the shortest path. But the difference between the Dijkstra and Bellman-Ford is that Bellman-Ford takes accounts of negative edges, which the Dijkstra doesn't. The limitation over Dijkstra is that it is slower compared to Dijkstra for non-negative weights, but necessary for graphs. And use cases used for situations where edge weights can be negative, representing scenarios with fluctuation connection costs. So here is the code of Bellman, and so here you can see the Bellman-Ford algorithm. So first, we have cleared all the uh, previous distances and previous edges. First, we have relaxed edges up to no up to n minus one nodes. Then we have checked for negative edge cycles that where all negative cycles are present, and then yeah, and then real-time updates. First, we have added an edge, and second, we have removed an edge, and third, update the weight of an existing edge. So these updates we have done to modify the output that will be shown.
So now this is our main functions, which includes all the file paths that we have passed into it. So now we will go through the output of this. So like first we can see the file, which output file is exported to this file, and then we are running the Dijkstra algorithm first from it. So it is running successfully. Then it is showing that it is running Bellman-Ford algorithm according to the graph. So yeah, it has implemented this, and now we have if we see the code, we have implemented the real-time updates in it. As you can see here, we have add an edge. So this is basically an example of real-time update. So here it is also giving output for real-time updates for both the algorithms.
So moving to the graph visualization part, we have incorporated various graphs and charts to explain our understanding and observations. So first graph is the showing all the edges and all the nodes that are present in the data set. Okay. So the key characteristics that are evident from this is that clustered communities, sparse connections between clusters, hub nodes, graph layout, edge weights, and yeah. So this visualization aids in understanding the community structure within Facebook dataset. Second is the degree distribution histogram. So degree distribution histogram is a visualization that shows the frequency of connections for edge in the network. In a social network, the degree of a node refers to the number of direct connections of friend each users have. Third one is the shortest path length histogram. The shortest path length histogram displays the minimum number of steps required to connect one user to another in the network. This visualization is generated by calculating shortest paths using Dijkstra and Bell-Food algorithms. The last is the real-time edge update visualization. So it is similar to the first graph. Just the difference is that certain nodes and edges have been updated. That generally happens from time to time. So it's a different graph from the first one. Thank you.